Okay, so welcome to class. We're on to section 5.5 and 5.6, and in section 5.5, we're just going to give sort of really some names to some stuff we were talking about in, with long division. So I remember I was sort of mentioning stuff about factors and remainders and things like that. We're going to sort of state some theorems that will help us with that, and then we'll also talk about the rational zeros theorem, which will help us discover certain zeros, right? So one of the difficulties with finding the zeros of a polynomial, say degree 4 or degree 3, is that it can be difficult to determine what the factors are, but we'll have a nice theorem today that allows us to figure out some of those details. I'm going to just sort of plow through 5.5 and not do any examples, and then I'm going to talk about the details of 5.6. So there's going to be a lot of sort of lecture heavy for the first 25 or 30 minutes or so. And then what I'm going to do is end the lecture by talking about a specific example where we sort of go back through all of the pieces. Because when we talk about rational functions in 5.6, really we're going to need to know how to find the zeros of a polynomial. And as a reminder, a rational function is just a ratio of two polynomials, polynomial in the numerator, polynomial in the denominator. Okay, so we've got some learning objectives for today. Again, the three theorems that we're going to want to be focused on are called the remainder theorem, the factor theorem, and then the rational zero theorem. The rational zero theorem is new, but the factor theorem and remainder theorem are just solidifying some things we talked about last time when we looked at long division. And all of this will help us find the zeros of polynomials, right? So using these three theorems, we'll be able to try to factor and find the zeros of a given polynomial. And we've seen that that can be incredibly important in terms of what the graph looks like and solving application problems. And then in 5.6, we'll turn sort of our attention away from polynomials and towards rational functions. And just again, as a quick reminder here, a rational function is something like this, p of x over q of x, where this is a polynomial and this is a polynomial. And you can almost determine a lot about the rational function right away by just looking at the degree of the top and the degree of the bottom and comparing the two of them. And so we'll talk about some of that. We'll introduce a little bit of what's called arrow notation. You'll need that for some of the homework. And we'll talk a lot about domain and how it's related to what are called vertical asymptotes. The domain's not related to the horizontal asymptote. That's a much easier thing to do where you just look at the degree of the top and bottom. And so it's a really fast sort of thing. But the vertical asymptote is much more detailed, and it will require you to come back to some of these ideas in section 5.5. And then the last thing we'll sort of say is just, you know, if somebody gives you a graph of a rational function and you can read off the asymptotes and the zeros, you can then write down an equation for it. And I think there's maybe 2 or 3 questions like this in Infinity. Okay, and like I said, I'm just going to plow through 5.5, not do any examples like you would see in Infinity, and then move on to 5.6, talk about some of those details, and then we'll sort of try and tie it all together with one big problem that uses all of the information, right? Because it all sort of builds up to the rational function stuff. By the way, we should already know how to find the domain of a rational function, set the denominator equal to 0. Okay, so let's talk a bit about the remainder theorem. And let me erase this and remind you of what we were doing last time, okay? So last time around, we started with a polynomial. In this case, I'm going to call it f of x. And it was some degree. And then we were dividing it by some other polynomial. And in the simplest case, it was x minus k, where k is just some fixed number. Okay. And so this would be the format that we were in. And what we did was we picked sort of values here and then went through this whole process until we got down to the remainder, which I'm going to call r in this case. Let me just jump back like this. I'm going to call that r. And up here we got the quotient. So I'll just call that q of x. And here everything is sort of arbitrary, so I'm not writing down any of the details. But we went through this process and got down to what this remainder was. And we know that the remainder in this case is a number, right? Why is it a number? Because this was a degree 1 polynomial, so this had to be something smaller, a degree 0, which is just a number. And we could rewrite this in the following way, right? We said that this was the dividend. That was the polynomial we started with. And it can be written as the quotient, that was that q of x, that's what we got for our answer, times the divisor, which is x minus k, and then plus the remainder, which was that r, okay? So that this information that we got from long division, like I was sort of pointing out last time, just tells you this, okay? And now what I want you to think about is what happens if I go through this whole equation and I replace every x with k. In other words, I compute f of k. Well, if I compute f of k, I'm going to get q of k. And then here I'm going to get k minus k. And then over here, that's just doesn't depend on x at all, so it's plus r. And what you should notice here is that k minus k is 0. Okay, and anything times 0 is just 0. So this equation really is f of k is equal to 0 plus r. In other words, f of k is equal to r. And that means that the remainder that we got here when we divided by x minus k is exactly f of k. Okay, so that goes by a name, and it's called the remainder theorem. And in Infinity, they'll ask you to use the remainder theorem to compute the remainder. What are they asking you to do? Just compute f of x, or f of k, whatever the k value is, okay? And you'll notice now that, for example, if the r were 0, right, if this was 0, then f of x can be factored into q of x times k minus x. So x minus k. X minus k would then be a factor of f of x, okay? So in the case that the remainder is equal to 0, and we talked about that last time, in the case that the remainder is equal to 0, we can conclude that this x minus k term is in fact a factor. And that also has a name. We call that the factor theorem. Let me go ahead and jump that. So that's the factor theorem. So what does the factor theorem tell us? It tells us that k is a 0 of our polynomial if and only if x minus k is a factor of f of x, right? And it follows from this fact over here. If the remainder were equal to 0, that would mean that the function had a 0, and therefore we could write it with this factor. And we talked about this last time. So what this theorem tells us is that if we know where a 0 is, if we could just get it from a graph or from some other means, if we can extract where at least one 0 is, well, then we know that x minus k, right? We know this x minus k will be a factor, and we can perform long division. We'll expect the r to be 0, and we'll get the other piece of the factor, okay? So that's what the factor theorem is telling us. So it's really nice if we know that k is a 0, okay? But it's not always going to be easy to determine what the zeros are. One way to determine the zeros, like we've seen, is just to graph it in Desmos and look for the zeros. But there are systematic ways, if you don't have a graphing calculator, for example, on the final exam, where you can extract a 0, right? Or what are the possible zeros? And what I'm going to show you here is just sort of working in reverse, right? So let's say somebody gives you a graph and they say, well, there's a 0 at 2/5 and there's a 0 at 3/4. Well, you should know by now that that means that x minus 2/5 and x minus 3/4 are both factors of the function that we're interested in. And if we multiply these equations by 5, or this equation by 5, we get 5x minus 2 is equal to 0. And if we multiply this one by 4, we get 4x minus 3 is equal to 0. And so if we just multiply those two factors together, we get a polynomial now whose zeros are either 2/5 or 3/4, okay? And then foiling this out, you get this big expression here. Okay, so I'm just going in reverse, right? I'm telling you that here is a polynomial with roots at 2/5 and 3/4. Those are rational numbers, the ratio of two integers. And you can rewrite it so that it's 20x squared minus 23x plus 6. And what we would like to do is have a method for going from this thing on the bottom, which is typically sort of how we write down a quadratic, and just trying to identify what is this number and what is this number immediately, right? And it turns out that we can't identify the exact zeros, but we can narrow the scope down, okay? And the way that we'll narrow the scope down is we'll take the leading coefficient, which in this case is 20x squared, and we factor it. In this case, 20 can be factored into 5 times 4 or 2 times 10, and we look at all the possible factors. So in this case, there's a 5 and a 4. And then we take the constant term, which is 6, and we factor it as well. In this case, 6 is just 2 times 3, and that's, I mean, I guess it could also be 6 times 1. That's the other way to factor it. And what we do is we use these terms here for the numerator. So that's where this 2 and this 3 come from. So if we were to track back this way, that's where the 2 comes from and the 3 comes from, these factors here. And then the denominators come from the factors of the leading term. And this in general holds true, right? If we were actually to multiply out terms like this and just do it with arbitrary coefficients, we would find the following result. It's called the rational zero theorem. And we're not going to use it just yet, but we'll sort of state it. So you want to determine the zero of some polynomial of degree n. So this is an arbitrary polynomial of degree n. And you want to find a zero. And in this case, we're just going to be interested in the rational ones. A rational number is just an integer divided by another integer. So not something like the square root of 2 or the square root of 3, but just ratio of 2 whole numbers. And it turns out that they're of the form P over Q. They're all of the form P over Q, where P is a factor of the constant term A0. So that numerator there is a factor of the constant term. And Q is some factor of the leading coefficient. So in order to use this theorem, we just factor the leading coefficient, and we factor the constant term, and we just put P over Q for every possible iteration. And again, I'm not going to do it quite yet, but we'll see it in the context of a problem, right? So remember, again, we just factor the leading coefficient, the final coefficient, and look at all the possible ratios. And there could be many, right? If A0 and AN have a lot of factors, you're going to be looking at, like, you know, a lot of different things here. So the example we'll look at doesn't have too many factors, but it narrows our list down to some finite list. Okay, so this is how we'll guess a zero. And then if we have one zero, we can factor it out and make the polynomial simpler and keep going through the process. Okay, so that's it for 5.5, okay? And again, I'm not going to do any examples quite yet. I want to show you how it's related to 5.6, because this is sort of the motivation for wanting to find the zeros of a polynomial. So when we're dealing with a rational function, rational functions will have two very important characteristics, right? So like the vertex for a quadratic, a rational function has a certain number of what are called vertical asymptotes, and possibly one or no horizontal asymptote. And what a vertical asymptote means is that as x gets closer and closer to some value, the y values of the graph tend to either positive or negative infinity, okay? So again, the output of the function goes to positive or negative infinity as the inputs, the x values, get closer and closer to some value of a. And it turns out that the vertical asymptote is a vertical line. And the way that we represent it or write it down is the equation of that vertical line. So it'll be actually x is equal to whatever that value of a is. And it's similar for the horizontal asymptote. So a horizontal asymptote just means that as we plug in y values that increase, right? So they get bigger and bigger and bigger and bigger, or they decrease, right? They get to like negative a million, negative a billion, negative a trillion without bound. So they go to either positive or negative infinity. Then the y values get closer and closer to this b. Right? So we get closer and closer to this line, y equals b. And we call this line a horizontal asymptote. So these are the definitions, but this is not how we'll determine if a rational function has a vertical or horizontal asymptote. So let's just look at, I mean, that's the word definition. Let's look at an example just so we can see it. So here's an example of a graph that is certainly not a polynomial, because a polynomial won't have a horizontal asymptote in it, it just can't. But this is an example of a rational function, and it has a vertical asymptote and a horizontal asymptote. Remember, the asymptotes are actual lines, right? And so when the homework system or on an exam, we ask you to write down the equation or find the vertical or horizontal asymptote, we're asking you for the equation of that line. So let me go ahead and ask the question for the chat. In this case, we have a single vertical asymptote. What is the equation for that vertical asymptote? Okay, so we can all see that it happens right there at x is equal to 2. It's over here somewhere, right there. Right here. Right. Okay, So right at x is equal to 2, and so the equation for it would just be x is equal to 2. That would be our vertical asymptote. And what about our horizontal asymptote? Okay, that one's going to be y is equal to 4. Okay. And again, we write them in this format because those are the actual equations of this line in red and this line in, in green. And again, what it means is that it's horizontal. If we get further and further to the right, we go further and further, we increase the value of x, the graph of the function gets closer to this green line. And also in the other direction as well. As we go out to negative infinity, we get closer and closer to this green line. Same thing when we're going sort of vertical, but we don't think about it as getting closer to the red line. We just sort of think about it as these numbers going up to infinity in this direction. And over here on this side, they go down to negative infinity. And just as a reminder, the vertical asymptote, you can go either direction. You can go positive infinity or negative infinity as you get closer and closer to that value. So in this case, that x equals 2 value, as we get closer to that, from the right-hand side, we go up to infinity. And from the left-hand side, we go down to negative infinity. And but these graphs can have, both of them going up or both of them going down, or one or the other going to positive or negative infinity. But we'll indicate that sort of piece of information with the arrow notation. So let me introduce a little bit of the arrow notation. Here we're going to focus first on that vertical asymptote at x is equal to 2. So there are two ways to approach 2. You can approach it from the right-hand side, So here we're looking at numbers that start at 6 and they get smaller and smaller and smaller, and we get closer and closer to 2. And you'll notice as we get closer and closer to 2, the values go all the way up to infinity. And we could also do it from this side over here. They would go down to negative infinity. But we indicate that as we come from the right, we go up in the following way, okay? So here we would say that x goes to 2 from the positive side. And what do we mean by the positive side? Well, it's from positive numbers, So we're going from the positive numbers this direction. And so as x gets closer to 2 from the positive side, f of x goes to infinity. So this is what the arrow notation means. And we can't put equal signs here because they're not values of the function. This is telling you what's happening as we get closer to 2. And then if we want to go from the left, okay, so now we're going from negative numbers to positive numbers. So we're going from the left to the right. The graph goes down to negative infinity. And so we would say x goes to 2 from the left. That's what that negative sign up there in the exponent means. And we approach negative infinity. Okay? And then when we're going to the other horizontal line here, what happens is this is when we go out to infinity in the right direction and out to infinity, to negative infinity in the left direction. And in both cases, we just go to 4, okay? So we would write this as x goes to infinity and f of x goes to 4, or as x goes to negative infinity, x goes to 4 as well. And that's what's meant by a horizontal asymptote. We're getting closer and closer to that fixed value. Okay, so that's the arrow notation. I think that's all I'm going to say about arrow notation. There are a few places in Affinity where they'll ask you about this. And again, you're just sort of looking for where it's going up and where it's going down. Yeah, Isaiah, the numbers can change. So this is just one particular example of a vertical and horizontal asymptote. Those crosshairs can sort of move around the graph all over the place. And there may be multiple vertical asymptotes, It doesn't have to be just one fixed vertical asymptote. Okay, so let's now review something that we previously talked about. So we've talked about rational functions and how they're a ratio of polynomials. There's a polynomial on top and a polynomial on bottom. And as we start to talk about vertical asymptotes, we're going to basically have the same idea as when we were looking for the domain. So we need to go back and remind ourselves of the domain. Okay, so Isaiah is asking, can it be as x approaches infinity, f of x is 4, and as x approaches negative infinity, x is equal to 6? That's an excellent question, Isaiah. In the case of a rational function, that will not happen. However, there are functions where you can have different values going out to the right or the left. And there's a really good one back from trigonometry. If you've seen some trigonometry, it's the arctangent function. So the inverse tangent function. actually has the feature that as you go to one direction, you get pi over 2, and as you go to the other, you get negative pi over 2. So it is possible, but not for a rational function. For a rational function, we'll see that there's sort of like either just one, and that's it, or none, okay? So that's a great question. But what we're after now is talking about or reminding ourselves of the domain. And this is where we're going to start tying back into 5.5 and the rational roots theorem and all that sort of stuff, okay? So remember, when we were looking at a rational function like f of x is equal to p of x over q of x, okay? So when we were looking at something like this, to find the domain, what we did was we looked at all the places where this denominator was 0, because we knew we couldn't divide by 0, right? That's the one thing we know we can't do with a rational function. And so we've got to throw out basically all of the numbers, the x values, the inputs that make the denominator 0. And that's what this reminder is up here, right? The domain of a rational function includes every single real number except those that make the denominator equal to 0. Okay? So we need to exclude this q of x guy sort of down here, right? Anything that makes that 0. And so the first step that we'll have to do in order to find the domain is set the denominator equal to 0. And if it's anything bigger than a degree 2 polynomial, we're going to have to use the stuff from 5.5 to figure out those zeros, okay? And we solve for the values of x that cause that denominator to be equal to 0. And then we write down our answer in interval notation, right, where we exclude certain values that made the denominator 0. And so we'll have to do a bunch of those union symbols in order to write down the domain. Okay, so that's how we found the domain of a rational function. And it turns out this is also the first step to finding the vertical asymptotes. Because everything that's not in the domain will either be what's called a vertical asymptote or what's called a removable discontinuity for a rational function. And I'm going to talk about how you distinguish between those two guys. And again, I'm still avoiding doing a problem until we get to the very end, because I want to do one that sort of ties all of the ideas together at once. Okay. So here's the domain of a rational function. And now let me just mention how it's related to finding the vertical asymptotes, okay? And let me just say, I guess, before I even go through the how-to, like why you're interested in the denominator being 0 for a vertical asymptote, okay? So if this thing is getting closer to 0, right? For example, if you divide a number like, say, 2 by 1/10, then when you divide a number by 1/10, something really close to 0, it gets bigger, right? So 2 divided by 1/10 is 20. And 2 divided by 1/100th is 200. And 2 divided by 1/1000th is 2000, right? So if I divide by a number that's getting closer and closer to 0 and the top stays fixed, then everything blows up, right? And so we get one of these vertical asymptotes where we're either going to positive infinity or negative infinity. That's provided the top stays fixed. If the top is also getting closer to 0, well then you don't have to blow up to infinity. And that's what we'll distinguish with in this how-to, right? So when does the bottom get closer and closer to 0, and when does the function sort of blow up to infinity? Well, you'll find it like this, okay? So you'll be given a rational function. You'll factor both the numerator and the denominator. You'll then identify the domain. So you'll set those factors equal to 0 in the denominator. And factoring the denominator will require the stuff from 5.5. But we'll find the zeros in the denominator, and then we'll have to go back and simplify our rational function. There may be some factors in the numerator and the denominator that match up, okay? And we need to cancel them all out. The ones that we cancel out, right, the ones that we cancel out are going to be holes in our graph, and we'll call them removable discontinuities. So we find all of those places not in the domain. And if we were also canceling it out, if there's a factor up in the numerator, then it turns out to be what's called a removable discontinuity. And it means that we didn't blow up to infinity, just a hole in our graph, right? An undefined piece of our graph. On the other hand, if it was just 0 in the denominator and we can't cancel out that factor in the denominator, then we say that we've got a vertical asymptote. Okay, so that's our vertical asymptotes. We just break them, we break the things that make the denominator into 0 into two parts, either the removable ones or the vertical asymptotes. The removable ones canceled things out. and the vertical asymptotes are things you can't cancel out. So that's the vertical asymptote. Now let's just say how we figure out the horizontal asymptote. So f of x is, again, something like p of x over q of x. And what you're going to want to do is look at the degree of the top and the degree of the bottom. Okay? And here they call it the numerator and denominator. Now, the first thing that you should be looking for is whether or not the degree on the bottom is bigger than the degree on the top. Okay? The way they say it here in this setup is the degree of the numerator is smaller than the degree of the denominator. And again, what that means is this is bigger, right? The bottom is bigger. The degree on the bottom is bigger. And what it means is that, for example, if you had something like, say, x squared over x cubed, well, when x is really big, x cubed is going to be way bigger, right? So, like, for example, if we had x as a trillion squared is way smaller than a trillion cubed. So when x gets really big, this thing's going to get closer and closer to 0, right? And what that means is that you'll have a horizontal asymptote at y equals 0. So that's the easiest thing to do, right? You just check to see, is the denominator have a bigger degree than the numerator? And if it does, you conclude that there's a horizontal asymptote at y equals 0. Okay, and it just means that this thing is taking over, right? When x gets big, it's just blowing up too much and making everything go to 0. The other possibility is that the degrees are the same. Okay? The degree of the top could be exactly the same as the degree of the bottom. So you might have something like 3x cubed over 5x cubed plus x. Okay? The degree on the top is the same as the degree on the bottom. And when that happens, what we want to focus on are just the leading coefficients, because these are all that will matter when x is really big. And you'll notice that in that case, the x cubes just cancel out. So when x is really big, everything gets closer and closer to 3/5. Okay, so that's the third part of this, right? When the degree of the numerator is equal to the degree of the denominator, you've got a horizontal asymptote, and you just take the ratio of the two leading coefficients, whatever they are, right? And it's because in the long run, everything in that x cubed over x cubed cancels out. And then the final thing here is, if the degree is just one more than the degree of the denominator, right? So if this is one more than the degree of the denominator, then we end up with what's called a slant asymptote. And I'm not going to do any examples of that, but on Monday, I think there's one question at Affinity about slant asymptotes. If you want to ask about them, we'll go through the process of how to figure it out. I think there's also a video in Affinity that helps you with the slant asymptote stuff. Okay, so let's do some examples now and finally do a few things, right? So going back to this one, let's now think about these three functions. We've got g of x, h of x, and k of x. And we want to determine if there's a horizontal asymptote, a slant asymptote, or just no horizontal asymptote at all, because it could be the case that there's no horizontal asymptote. When does that happen? Well, it happens when the degree of the top is bigger than the degree of the bottom, right? So that was one of the, out of those three cases that we had before, that's the one thing that didn't show up. And in that case, you just don't have a horizontal asymptote at all. Okay. So let's look at the first one. And let me ask first, does this thing have a horizontal asymptote or not? So this is just a yes or no. Yes, it has a horizontal asymptote, or no, it does not. What do you guys think? Okay, so everybody is seeing that the answer is yes, and that's because the degree of the top is equal to the degree of the bottom. Okay, so the answer indeed is yes. For A, we do have a horizontal asymptote. And the formula for the horizontal asymptote, right, when x gets really big, it just looks like the ratio of the two leading terms. Okay, so what is that ratio of the two leading terms? What do we get? Y equals what? Yeah, so if we just look at the two leading coefficients, it's 6 over 3, right? I'm sorry, not 6 over 2. So there's a 6 there on that first one, and the bottom one is a 2. And we're going to put x cubes here and an x cube there, but they just cancel each other out. And 6 over 2 is 3, so it's just y equals 3. So when x is really big, if we were to plug a really big number into this rational function, like 1 billion, the number would be really close to 3. Right? And that's what we mean by a horizontal asymptote. Okay, so that's the sort of that first one. What about k of x? Does this one have a horizontal asymptote, yes or no? So yes, it does have a horizontal asymptote, or no, it does not. Okay, so I see a lot of no's. I'll go back to our statement here. So Victoria says y equals 0. So I've had a lot of no's, and then Dalton is now saying yes. What do you guys think? Which of these 3 cases are we in here? Is it the first one on top, the middle one, the last one? Okay, so I think a lot of people are seeing that it's yes. So the answer is it's yes, right? So what we're seeing is that the degree of the denominator is bigger, right? That x cubed is bigger than the x squared. And because of that, the x cubed will just take over, right? So this was part A. For part C, because that degree on the bottom is bigger, we just have a horizontal asymptote at y equals 0. Okay? So you just want to look at the degree of the bottom and top. Now, what about B? Is there a horizontal asymptote, yes or no? So yes, there is a horizontal asymptote, or no? Yeah, everybody's right here. The answer is no, because the degree on the top is bigger than the bottom. However, it's just one more. So this would be what we call a slant asymptote. It's not a horizontal asymptote, but a slant asymptote. And I'll talk a little bit about the equation on Monday if people are struggling with it in the homework. There's only one question in that case. But if the question is it a horizontal asymptote, the answer is no. Okay? So you can answer everything about horizontal asymptotes just by looking at the degree of the top and bottom. No factoring needed. Okay? So that's that piece. Now, let me go ahead and do an example, and then you'll notice there's one more slide. So we need to talk about one last slide after we do this example. But this is the example I wanted to say that we're going to sort of do all of the different things from 5.5 all the way through 5.6. And what we're going to do is we're going to find the zeros of f of x is equal to 2x cubed minus x squared minus 2x plus 1. So we're going to work on that. That's stuff from 5.5. And then we're going to sort of shoehorn this into the denominator of a rational function in our next question. Okay? But right now, I just want to find the zeros. So I want to set this thing equal to 0. And in essence, they're asking you, can you factor this thing? We could try factoring by grouping in this particular case. And if you saw how to factor by grouping, that might be a good way to do it, but maybe you didn't, okay? So what do we need to do here? Well, we need to first guess a 0, right? And the way that we're going to guess a 0 is to use the rational 0 theorem. So rational 0 theorem. And remember, those were roots of the form P over Q, where P and Q are integers. And we can guess the form of all of them, right? There's only going to be finitely many. And the way that you do it is you focus on the factors of the leading term and the factor of the final term over here, okay? So here, the factors of 2 are what? What are the possible factors of 2? Thanks, Isaiah. Yeah, we've got I squared, right? What should we get for factors of 2? So 2 and 1, right? But when we're using the rational 0 theorem, we also have to include the possibility that they could have been positive or negative. Because we could do -2 times -1 and get 2, right? So we have to go through 4 possible roots here. +2, -2, I'm sorry, factors. +2, -2, +1, and -1. And if this number was something like 6, we'd have to do 1, 6, 2, 3, and plus or minuses for each one. So there'd be a whole bunch of different combinations, and it can get sort of annoying the more factors there are. But the next thing we have to do are the factors of 1. What are the factors of 1? And there's more than just one of them. Yeah, so it should be plus or minus 1. That's right. So positive 1 or negative 1. And why negative 1? Well, we could multiply negative 1 times negative 1, and we get 1. So it's a factor of 1. And what this means is that we can now write down the possible rational roots, right? What are the possible rational roots? Well, these guys are the denominators, right? Those are the factors of the leading coefficient, and these guys are the numerators. So one possibility would be 1 over 2, like 1 over 2, and then another possibility would be 1 over 1. Okay, but then these could be negative as well. So we could have got 1 over negative 2 or 1 over negative 1. Okay, and there's still a few more, right? We could have got negatives on the top. So we could have got negative 1 over 2, negative 1 over 1, negative 1 over negative 2, and negative 1 over negative 1. But you'll notice that those are all equivalent to these, right? Because if you have two negatives, it's just the same thing as the positive. So the rational zero theorem tells us that the following are potential zeros. So we can narrow down the search for zeros as 1/2, 1, negative 1/2, and negative 1. So what you're saying is that it will always be the first and last number. Yeah. So it's always either the leading coefficient and then the constant term, and you factor both of them, right? The factors of the tail end are the numerators, and the factors of the leading coefficient are the denominators. And it comes from that fact that when you multiplied everything out, right, with those factors going in reverse. So remember, I sort of did that one example where we went sort of in reverse. The reason is that these are the potential ones, okay? So now we say, okay, these are the possible zeros. It doesn't mean that they're all zeros, but these are the possible zeros that are rational, and there's only 4 of them. And it gives us a step into factoring this guy, right? Because really, if we're going to do something with a rational function, we're going to have to factor. So what we should do now is start to guess, right? Which of these are going to be the easiest to check if it's a zero? Which number should we start with here? Yeah, I think everybody can see that 1 is usually the easiest thing to work with. And so we'll just check to see if it's equal to 0. And if it wasn't equal to 0, we'd have to go on to another one, okay? So here, let's just plug in f of 1 and check to see, does it equal 0? So we get 2 times 1 cubed minus 1 squared minus 2 times 1 plus 1. And here you have positive 2, here's negative 2. Here you have negative 1, here's positive 1. So indeed, it does equal 0. So this is a 0. But for example, if you were to have plugged in negative 1, it wouldn't be a 0, right? It's just a possible 0. We have to check to see that it's equal to 0. And what this means is by the factor property, or by the factor theorem, x minus 1 is a factor. Okay. So now we know that x minus 1 is a factor of this polynomial. And we can go through and find the quotient, okay? How do we find the other piece? Well, we divide, okay? We're going to take this expression and divide it by x minus 1. And by the remainder theorem, because this is a factor, we should expect the remainder to be 0, right? So we're going to go through the whole process of long division now, and we'll get a nice remainder of 0. Okay, so we know that this x minus 1 term is a factor, so we take x minus 1 and we divide our polynomial by x minus 1. Okay, and last time we really sort of focused on long division, so I'm going to go through this pretty quickly. Here, in order to get the 2x cubed, we need a 2x squared. So that gives us a 2x cubed minus 2x squared, and then we subtract. So here we're going to get negative x squared and then minus a negative 2, so that's positive 2. So we get an x squared there, and we bring down our negative 2x. And now we need the x squared to go ahead and match up. So here we need to put an x, so that x times x becomes x squared. But then x times negative 1 is minus x. We subtract this process. Again, the x squareds cancel. Here we have negative 2 minus negative x, so that's plus x. So that's negative x, and then we bring down the plus 1. And then finally, to match this negative x, we need to multiply by a -1. So that gives us negative x plus 1. We subtract, and then we indeed do get 0. Well, so I'll point out why we're doing this. Remember that when the remainder is equal to 0, what this formula is telling us is that f of x is equal to x minus 1 times the quotient, that 2x squared plus x minus 1. Okay, so this information that we have right here is telling us that it factors into this format. We would normally put plus the remainder, but the remainder is 0. Okay, and we knew that we were going to get 0 here because we used the rational zero theorem to get that 0. So once you know what the 0 is, you divide and you get your quotient, and that's the first step in factoring this f of x. Okay, so we have to know how to do long division in order to get this thing factored. Okay, but we're still not done here because we were looking for the zeros. So now we have to factor this piece as well. Okay, so let's go ahead and go through and factor that piece as well. So again, it's this 2x plus x minus 1, and it's times x minus 1. So we just showed via long division that this is true. We can rewrite this f of x in this way. And now this is a good old quadratic, so we can go ahead and factor that guy. So we're now going to get x minus 1, and we're going to factor it into two pieces. This is a 2x squared, so one of these should be a 2x, and one of them should be an x. This is -1, so the only factors are 1 or -1. And because this is negative, one of these should be positive, and one of them should be negative. So should this be positive or negative? Yeah, Destiny, all of this is part of finding the zeros. Yeah, this one should be positive, and this one's negative, okay? And again, I'm just factoring this piece out. And now we can find the zeros. Once we factored the thing completely, we get x minus 1 is 0, 2x minus 1 is equal to 0, or x plus 1 is equal to 0. This one gives me x is equal to 1. This one gives me x is equal to 1/2, and this one gives me x is equal to -1. So these are the three zeros of this quadratic. We had to guess this one, perform long division to get the quotient, and then factor the quotient. Now, one thing that might happen is you might not be able to factor this, and if you can't factor this, you can set it equal to 0 and use the quadratic formula, and you may end up with complex numbers as some of your roots. There are some questions where they ask you to get complex ones, but if you can factor it into two pieces, you can set all the factors equal to 0. And indeed, this is all of the work that you need to do in order to find the zeros of this polynomial. Okay, so how does this tie back into a rational function? Well, remember, in a rational function, you have a polynomial on the top and a polynomial on the bottom. So if you're going to find the domain and the vertical asymptotes, you're going to have to set the denominator equal to 0. And that's essentially what we've done in this problem, right? So the first step in finding vertical asymptotes is to set the denominator equal to 0. So I'm going to use this as my denominator in my next example so that we don't have to go through a whole nother problem where we do that. And I'm going to refer to the previous steps, right? So here's our second example. We're going to let f of x be equal to x squared minus 1 over 2x cubed minus x squared minus 2x plus 1. And the instructions here are to first find the domain. Second is find the horizontal asymptotes. And then C is find the vertical asymptotes and removable discontinuities. And remember, the things that we remove from the domain are going to be of one of two types. They're either going to be vertical asymptotes or removable discontinuities, depending on whether or not we can cancel things. So let's go through this whole process, and I'm just going to point out that this is the easiest. We don't have to factor anything at all in order to answer this one. Where is our horizontal asymptote? There's one in this case. right? It's at y equals 0. And that's because the degree of the top is equal to 2, and the degree of the bottom is equal to 3. The degree of the bottom is bigger than the degree of the top, so we've got a horizontal asymptote at y equals 0. And it makes sense. When x is really big, all of this stuff over here doesn't really matter. All that matters is x squared over 2x cubed, and x cubed is way bigger than x squared. So as x gets really big, everything's going to get closer to 0. Okay? And we can just see that by looking at the degree of the top and the degree of the bottom. Okay, so we've dispensed of this one pretty quickly, and we don't need to factor anything to do it. However, to find the domain and to do these two things here, we need to actually take the denominator and set it 0. But luckily, we've already done that in our previous example. Okay, so we need to let 2x cubed minus x squared minus 2x plus 1 be equal to 0. That's our first step in finding the domain, because we want to remove anything where this is equal to 0. And so by the last problem, we found that this was x is equal to a half, x was equal to 1, or x was equal to negative 1. And we had to do all of the steps in the last problem, right? We have to use the rational zeros theorem. We'd have to then do long division. We then have to set all of the factors equal to 0 just to do this first step, right? That's what those dot, dot, dots mean. So we did that in the last one. And now we can write down the domain. So the domain is going to be everything except for these three values, because if I plug those in, the denominator is 0. Okay, so let's go ahead and write this out. It's going to go from negative infinity to the smallest value, which is negative 1. And then it's going to go from negative 1 to the next smallest, which is 1/2. And then it's going to go from 1/2 all the way to 1. And then finally from 1 to infinity. This means we've removed negative 1. This means we've removed a half. And this means we've removed 1. Okay? And we write it as a union of all of those various intervals. So we know the domain is this. And we now have to go through and determine if these zeros are either vertical asymptotes or are they just removable discontinuities? Are they just holes in the graph, right? A place where the function is undefined. And the way that you do that, right, the way you distinguish between these two is you now have to factor the top. And if one of the factors cancels out, it's a removable discontinuity. And if the factor doesn't cancel out, well, then the bottom's going to get closer and closer to 0, and the whole thing will blow up to a vertical asymptote. So let's go ahead and do that now, right? So we already talked about in this step how to factor the denominator. Now we're going to factor the top. What is the, if I factor the top, x squared minus 1, what does it factor into? Remember, that's the difference of squares. X squared minus 1. Okay, so I see Jordan has put x plus 1, x minus 1. Okay, Destiny as well. Yeah, it's just the difference of squares, x plus 1 times x minus 1. And then down here in the denominator, we saw that it was x minus 1, that was the factor we guessed. And then we had a 2x minus 1, that was leading us to 0 or 1/2. And then we had an x plus 1. Okay? So this is the rational function completely factored on the top and the bottom. And if we're going to simplify it, we can see that this x plus 1 cancels with this x plus 1. So as this gets closer to negative 1, like as this gets closer to 0, so does this. So it's not going to blow up like we saw before, okay? This x minus 1 will cancel this x minus 1. So as this gets closer to 0, so does this. And so these are both removable discontinuities. On the other hand, this 2x minus 1 doesn't get canceled on the top and the bottom. So as this gets closer to 0, the whole thing just blows up, right? Either the positive infinity or to negative infinity. And we can write this in the following way. It's 1 over 2x minus 1 if x does not equal 1 or x does not equal negative 1, right? Because this equality only holds when x is not equal to negative 1 or 1. Okay, so that means we've got removable discontinuities at x is equal to 1 and x is equal to negative 1. And we've got a vertical asymptote at x is equal to 1/2. Okay, so we can expect that at 1/2 this function blows up, and at 1 and -1, it has a big hole. There's nothing in the domain there. Okay? And then we also know what happens when x goes out to infinity. Because this degree is bigger on the bottom, it goes to 0 when we go to the positive direction, and 0 as we come back to the negative direction. And I think I'm just going to go ahead and stop there with this setup, and that'll be the video for today. So have a nice day, guys, and make sure you check out that email I sent out.